In mobile robotics, navigation combines perception, mapping, planning, and control. The robot must avoid dynamic obstacles such as humans. This requires predictive modeling of other agents' behavior. Social navigation introduces additional complexity. The robot must move in ways that are socially acceptable and predictable. Human-robot interaction is another domain where AI plays a major role. Robots must interpret human speech, gestures, and intentions. Natural language processing and computer vision models enable multimodal interaction. The robot may maintain a belief state about the human's goals and update it as new information arrives. From a systems architecture perspective, AI in robotics often runs on heterogeneous hardware. Real-time constraints require efficient inference. Edge computing devices, GPUs, and specialized accelerators are integrated into robotic platforms. Latency and power consumption are critical design factors. Let us examine the concept of embodiment. A robot's intelligence is shaped by its physical form. A quadruped robot has different capabilities and constraints than a wheeled robot. The morphology influences the control problem and the learning problem. AI models must account for the robot's kinematics and dynamics. Model-based versus model-free approaches represent another important distinction. Model-based methods use explicit models of the robot's dynamics to plan and control. Model-free methods learn policies directly from data without an explicit dynamics model. Hybrid approaches learn models from data and use them for planning, combining the strengths of both paradigms. Explainability is particularly challenging in robotic AI. If a robot behaves unexpectedly, engineers must diagnose the cause. In modular systems, the fault may lie in perception, planning, or control. In end-to-end systems, the mapping from input to action may be opaque. Techniques such as attention visualization, saliency mapping, and intermediate supervision can provide insight. Scalability is also a concern. A robot trained for a single task in a single environment is limited. The goal of general-purpose robotics is to create systems that can perform a wide range of tasks in diverse settings. This requires transferable representations, meta-learning, and continual learning. The robot must learn new tasks without forgetting previous ones. Continual learning introduces challenges such as catastrophic forgetting, where training on new tasks degrades performance on old tasks. Techniques such as rehearsal, regularization, and modular architectures are used to mitigate this. Multi-robot systems introduce additional AI challenges. Robots may need to coordinate, share information, and allocate tasks. Distributed planning and communication protocols become essential. Swarm robotics explores decentralized coordination inspired by biological systems. Ethical considerations in AI robotics are profound. Autonomous vehicles must make safety-critical decisions. Industrial robots must coexist safely with human workers. Surveillance robots raise privacy concerns. Governance, standards, and verification frameworks are necessary to ensure responsible deployment. Verification and validation of robotic AI systems are complex. Traditional software can be tested exhaustively in limited domains. Machine learning components, however, generalize from data and may fail in rare edge cases. Simulation, formal methods, and scenario-based testing are used to evaluate performance under diverse conditions. Energy efficiency is another important aspect. Mobile robots rely on batteries. Computationally intensive AI models consume power. Efficient architectures and hardware-aware optimization are necessary to balance intelligence and endurance. Let us consider the integration of symbolic reasoning and learning. Classical AI emphasized symbolic representations and logical reasoning. Modern AI emphasizes data-driven learning. In robotics, combining both can be powerful. High-level task planning may use symbolic representations of goals and constraints. Low-level perception and control may use neural networks. Bridging these levels is an active research area. Cognitive architectures attempt to model perception, memory, planning, and learning in an integrated framework. For robotics, such architectures must operate under real-time constraints and interact with uncertain environments. Robotics also provides a testbed for embodied intelligence research. By grounding AI in physical interaction, researchers can study concepts such as affordances, where objects are understood in terms of possible actions. A chair affords sitting. A handle affords pulling. Learning affordances requires linking perception with motor capabilities. In industrial settings, robotic AI enables flexible automation. Instead of programming fixed trajectories, robots can adapt to variations in object position and orientation. Vision guide manipulation and force feedback enable more robust operation. In healthcare, robotic systems assist in surgery and rehabilitation. AI algorithms analyze sensor data to provide precision and adaptivity. Reliability and safety are paramount in these contexts. In agriculture, autonomous robots perform tasks such as harvesting and monitoring crops. These environments are unstructured and variable, requiring robust perception and planning. The future of AI in robotics likely involves tighter integration of learning and control, improved sim-to-real transfer, richer multimodal perception, and more general-purpose capabilities. Advances in foundation models may enable robots to leverage large-scale pre-trained representations for language and vision, enabling more natural interaction and flexible task specification. In conclusion, AI in robotics is the convergence of perception, planning, learning, and control within embodied systems operating in the physical world. It requires managing uncertainty, ensuring safety, optimizing computation, and integrating diverse algorithms into coherent architectures. For a highly technical audience, the key is to view robotics not as a single algorithmic problem but as a systems-level challenge where AI components must function reliably under real-world constraints. Understanding these architectural principles is essential for building the next generation of intelligent machines that can perceive, reason, and act autonomously in complex environments.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.